very excited to be here. Thanks, Beth and Refactor, for having me. I am very happy to share with you a personal obsession of mine. Feels like every time I'm at this conference, it's like that. So it's a bit of a therapy session for me. This is the outline of the talk. Inspirations, my inventions, record replay, time travel debugging techniques, omniscience. Let's get into it. This is Brett Victor, and here he's giving a talk entitled "Inventing on Principle." And to me, this is probably an all-time classic in computer science. Any Brett Victor fans out there? Okay. So here he's demoing a video game, but it's not just a video game. It's actually a development environment for a video game where you have access to this scrubbable timeline at the top that can allow you to reverse time. And not only that, you can actually make changes to the program, like that velocity value that he's showing. And when you make a change, then you scrub the timeline again. Everything just adjusts to the new value. But there's another mode where if you click it, you can actually see the position of the character during all points in time in the entire run of the program. And not only that, you can still make changes to this value, and as soon as you make a change, you can actually see the position of the character change in all points in time, including past and future. Well, just the future, I think. So this was crazy. This is kind of life-changing for me to see this demo. Another inspiration of mine is Redux. So this is, as I understand it, how the core of Redux works. So the program is going to keep track of some state of the program. We're going to call that the current state. And in order to make any changes to the program, you're going to have to go through this reducer. So you'll take your current state and you feed it into the reducer as the previous state, along with an action. And an action is an ambiguous way to specify how you should make a change to the previous state. And then out comes the next state, and then you grab the next state and you stick it back into your current state. And that is how you should work with your program. One thing to note is the reducer should be implemented as a pure function, which means it shouldn't make any changes to the previous state. Instead, it should spit out an entirely new object as the next state, which means you can actually, when you get an update, which is one of these arrows on the top, when you get an update and you generate a new state out of it, it doesn't have to change the previous state, which means you can actually keep track of all intermediate states of the program as you go. And that has huge consequences. So around 2019, I was working as a mentor, and I helped developers debug some complex problems. And I was contemplating this, and I realized that debugging is hard. Print debugging versus breakpoint debugging. Show of hands. Print debugging, anyone? Breakpoint debugging, anyone? Okay, it's actually 50-50. Okay, so gonna rant a little bit, or just, you know. So print debugging, what are the problems with print debugging? Well, it's tedious, that's one. And also it feels dirty because you're not really gonna wanna check that in, right? This code is temporary in nature, and all of the developers I work with, they don't really wanna do it because it's like, it feels temporary. And another issue with it is when you have too many logs, it becomes difficult to sift through all the volume of logs. Breakpoint debugging, or step debuggers. The main problem with using a step debugger is that choosing a breakpoint is like playing The Price is Right. You want to try to get as close as you possibly can, but without going over. which is the reason the contestant on the right has elected to stop the program at line number 1. And the hardest part about debugging is Heisenbergs. Bugs. A Heisenberg is a bug that when you try to look closer at it, it just goes away. How are you going to fix a bug if you can't even get your hands on it? Okay, around the same time, I was working on a side project. It's a programming language that I made, and I realized on vacation, I was contemplating in a contemplative mode, and I realized I could actually build the architecture of something like Redux directly into the core of the language, and thereby enabling statement level time travel debugging. So I did that. A lot of the work was spent during my vacation when the time I was up because I was jet lagged. So which brings me to the first way to time travel. So if you look back at this timeline, and if we model this sort of state timeline, and if we put all of the state of a program into any one of these state objects, and that includes all of your variables, the stack frame of the program, any heap objects, and any threads if you have them. And we save all of those in every single one of these state objects on the timeline. We save them off. Then we would get time traveling for free because it's very easy. You just have a cursor, you point to state 0 versus state 1 versus state 2, and then you get transported back to that point in time in the program. Easy. So that's what I did. I did a proof of concept, and my programming language was like a transpile to JavaScript language. This is me doing a demo. I started out with very simple programs, and then I moved to more involved programs. This is a tic-tac-toe AI, which incidentally, it beat my friend Hui Qi here. So it's like, yeah, and it used substantial computing resources. At first I ran this, it ran out of memory right away. And it took a lot of re-engineering to make this work. I will show you a debugging session of this game later on in this talk. So first method has some obvious drawbacks. If you're going to save every single intermediate state of the program and the program changes a lot or the program has a lot of state in it, that's going to take a lot of space. So another way to do it is instead of saving every single state, you could save every update instead. And presumably the update will take a lot less space to store. And so what you could do is you start with state 0, which presumably you can sort of infer what that is. And then you replay every single update on top of it to regenerate the intermediate states after the fact. So I took this approach with Python. I brushed up on my C programming skills, and I opened up the Python interpreter, and I found every place that would make a change to the state of the program, and I wrote it to a log. So you would run your Python program like this using the PyRewind is the name I gave to my sort of mod of Python. So you run your Python program, it'll generate a log file like this, and then there's a program that would read back this log file and recreate all intermediate states of the program and store it in a SQLite database. And then with this SQLite database, you can use it to debug the program. So you use this debugger user interface, which works like a normal step debugger, but you can step either forward or backwards in the program. But a key difference between this debugger and the normal ones that you would use is when you're stepping through, it's not actually executing the program. It's merely moving back and forth within the pre-computed states that are already stored in this database. I got very excited about this when I made this work. It was like one of the highs in my life. I shared this with my former professor, Mark Gustow. And Mark Gustow, he used to be my professor at Georgia Tech, and I credit him with making Python the de facto standard for computer science education. But he pointed me to a bunch of prior work in this area. So it turns out there's other people that have done this thing before me. um, and it was very humbling, but I also I like the fact that I kind of did this deep dive with a beginner's mind. I think to some extent it's more fun that way. But so I was reading these papers. I did a deep dive into the academic literature and also some sort of commercial products that were doing this. And reading some of these papers made me feel a deep connection to the authors because they had to sort of force themselves to solve some of the same problems that I had to go through. And it was, it gave me the warm and fuzzies. But on the other hand, I did feel like a small fish in a big pond. So record replay is what RR stands for. RR is a C and C++ debugger that works only for Linux, unfortunately. Anyone using Linux? One Mark uses Linux. Okay, Mark, try this out. So I just stumbled upon this and I was really amazed and got so excited. And I was actually able to use this for my Python debugger work because Python, as you know, is written in C. And it really made me feel like I am living in the future when I use this. It's the first production level time traveling debugger that I have been exposed to. And not only did it help me solve very complex problems, it also was a very helpful tool for me to learn a complex code base that I hadn't seen before. How does it work? It uses a technique called deterministic replay. And if you wanted to learn more about this is the term to Google. So it's based on the idea of determinism. So most programs are deterministic. So if you run this program 100 times, it'll spit out the same thing every single time. So because it's deterministic. However, there are sources of non-determinism. You don't know ahead of time what the user is going to do. So what are you going to do? These are some sources of non-determinism that you might run into. What are we going to do about that? We're going to model our program as a deterministic machine that is going to interact with the non-deterministic world. Okay. So in this example, we start our machine, and then the machine is talking to the non-deterministic world via sending back and forth these messages. What we can do is record every message it receives from the world, along with like the content of the message, but also the timestamp at which it received that message. So, and we save it off somewhere in a file. And then after that, what we can do is rerun the program, but this time don't connect it to the world. We just connect it to a pre-recorded tape that plays back those messages at the exact precise time as the first run. So in the first run, we're going to call this, we run the program in record mode. And then here, when you're debugging the program, you're going to play it in replay mode. And what you notice is when we're running it in replay mode, everything about the system is deterministic, which means no more Heisenbugs. So now that you have this record replay system, how are you going to get a time traveling debugger out of it? Well, let's say we run this program And let's say the user, when we run it in record mode, the user typed in 7. We're going to take that 7, save it off in a file. We're now going to run it in replay mode. So when it comes across this input, we're just going to supply the pre-recorded response as 7. Now we're going to unroll the loop, and we're going to number every single statement. So let's say now we use a step debugger, and we're paused on line 16. If we want to walk backwards in time, what we can do is we set a breakpoint at line 15, and we start over from the beginning. And we hit 15 again, and now we have simulated going backwards in time. Obviously, that's a overly simplified explanation. If you want all the full details, you can read their technical report. This is another record replace based debugger. It's called Replay.io. It also comes from Mozilla, as did RR. So this project is very much a sibling of RR. And this debugger is for JavaScript. It's based on the Firefox core, and it features a video playback of the actual web page, as well as a retroactive console.log statement. Okay, so along the way of sort of developing this technology and also using it, I've sort of come across a few techniques that I use with the time-traveling debuggers. I'll show you a couple of those. The first one is called backup and drill down. So if you have some code like this, what you can do is, so like this is like the top level of the code. Like you can look at the top level of the code as the outline, but you could drill down to the specific lower levels. And the problem a lot of times is, again, choosing the breakpoint. But you don't have to choose with a time travel debugger. You can just casually step through every line, because you can just go back. So and you can, after every line, you can sort of assert or observe the result to see if there's anything wrong with it. And let's say you found something wrong here at this step. Maybe the summary object is somehow wrong, not what you expect. Then you just go backwards to before the summary was generated, and you can drill down to the thing that actually generated the summary. And that takes almost no time. So we solved the Price is Right problem. Another technique is called start at the end. So let's say you encounter an error in your program. What you can do with a time travel debugger is you start the program at the location where the error happened, and then you just go back one step. And in this instance, I went back one step. I realized I hit the wrong branch. I should have came from a different branch for the number 11. I should have gone to the num greater than 10 branch, and this was the wrong one. So those are some of the things that are possible with time-traveling debuggers, but there's more. Bill Lewis is the person I consider the father of time travel debuggers. So in this paper, he coined the term omniscient debuggers. The word omniscient means all-knowing, and he uses it to mean the debugger knows about the state of the program at all points in time beforehand. And when you have this ability, it gives rise to possibilities that were unimaginable before. This is actually, the Brett Victor example is actually one instance of this, where you actually just see the position of the character at all points in time, and you see all of them at the screen at the same time. I'll show you Bill Lewis's ODB, where he has a history timeline, okay, or history outline, sorry. So I'll zoom into the outline. So this is the history outline. It looks like a stack trace, but whereas most stack traces, they only indent to the right, this one indents to the right and then outdents back to the left. It sort of looks like an HTML file, right? And the reason you can do this is because we have already ran the program from beginning to finish. So every function that has started we also know how it has ended. So you're essentially seeing like an outline of the entire program. It goes in and then it goes back out. And here, I had a Zoom call with him and he's demoing this to me. So you can click through different parts of the outline and it jumps you straight to the line of code in the middle here. It jumps you straight to the line of code that part is associated with, as well as you can see the scope and all the variables at that point in time immediately. I took this concept and I kind of put a different spin on it. So this is a zooming user interface for visualizing the history of the program. And this rectangle here is the entry point of the program. And if we zoom down enough, you can see the details within that function to see what occurred in the function. And we're going to zoom in again to the play game function. And here, this is the, oopsies. All right, start again. So this is actually the tic-tac-toe game that the AI played with Huiqi earlier. And you can actually see at the high level how the game progressed. You can see each move that was played. And if you want to figure out how the computer arrived at the move it played, you can drill down more to where the calculation happens. So here you can see the computer is trying out a few different moves. And after it computes a possible move, it then is trying to calculate on behalf of its opponent what the opponent would calculate based on that move, and so forth. Another feature in the ODB is the object timeline. So given any heap object, like an array or a dictionary, he actually has this fast forward and backward button that will jump you to the moment in time when this array next changed, or the previous time when the array changed. And it'll jump you to the line of code that caused that change. And this is incredibly powerful because so many times in debugging, you're seeing this erroneous value and you're asking the question, how did we get this value? And this will give you the answer instantly just by pressing a button. Finally, I want to show you another omniscient debugger called Pronosco, which comes from the makers of RR. They have a data flow feature where you can click on a value encounter in a program. Say you're getting an unexpected null value. You can click on that null value and it'll give you immediately all the causal steps, all the assignments and memory copies that led to this value being what it is at this moment. This is something you would have had to do a lot of detective work backwards yourself, and it has just automated this for you. Another feature is the call history. So in Pronosco, you can search for a function name, and it will give you a list of all the times that this function has been called during that run of the program. And you click on this list, and then immediately be transported to where that function is called. And you can see the stack frame, you can see all the variables, everything like a normal step debugger. So looking back, it occurred to me that a lot of the most important sort of advances in computer science are actually coping mechanisms for the fact that debugging is hard. And if you think about all of the hours that humanity has put into these projects, what if we use some of that and try to solve debugging? What if debugging was not hard? What would computing be like?